In this chapter, we will be introducing the concept of radicals. In this video, we'll be learning how to divide radicals, including how to rationalize monomial denominators.
Okay, hi everybody. Well, we've added and subtracted radicals, we've even multiplied radicals, so now you know we got to divide radicals. And we're going to take this in kind of baby steps here because this can get a little bit complicated. Division always is. You think back to when you were learning long division way back when, it's tough. Okay, so dividing radicals takes just a little bit more. But having said that, to start off with, the pattern's not too bad. In fact, it's going to be a little bit familiar. Remember that when we multiplied radicals, we had something like this. We would take a root b, and we multiply it by c root d. That what we got here was ac multiplied by root bd. And so what we would do here was we would multiply the coefficients together, and then we would multiply the radicands together and keep them inside the radical. Well, actually, we do the same thing here. In fact, if we were going to kind of compare it to what I just did, if we had a root b divided by c root d, another way we could write this would be a over c multiplied by the square root of b over d. And then what we could do is we could simplify that fraction, we could simplify that fraction to get it down to as simple a form as we can. Okay, that's kind of where we're going to start when it comes to dividing radicals. Okay, so now we're going to take a look at a bunch of examples. Okay, here we go. Let's take a look at some examples here. So divide and simplify each of the following. Okay, so to start off with, we've got this square root of 70 divided by the square root of 7. Now, notice in both cases the coefficients are 1. So 1 over 1 would be 1. But now what I'm going to do is I'm going to rewrite that as root 70 divided by 7. Okay, now I can focus my attention on cleaning up that radical here. And I know that 70 divided by 7 is 10. And so this is the same as the square root of 10. And now when I think back to root 10, 10 has got the factors 2 and 5. And so that since there's no pairing up of factors in there, that is as simple as that's going to get. Good, so I can move on. Take a look at this one. 30 root 6 divided by 15 root 2. Okay, well, I know that I can split that up into two expressions here, 30 divided by 15, and then the square root of 6 divided by 2. And then I treat them separately here. So 30 divided by 15, well, that's easy. I know that that's equal to 2. And 6 divided by 2 is 3. And so I'm left with 2 multiplied by the square root of 3. Now, I can't go any further than that without using the calculator, so I'm done. Okay, that's as far as I want to go. And it's easy because 3 is a prime number, so I can't break that down into anything smaller. Okay, here we go. Negative 25 root 40 over 5 root 5. Okay, well, first of all, I'm going to, whoops, and I have no idea why I did that. Okay, so I'm just going to, cross that out there. That's not at all what I meant. I meant to write negative 25 divided by 5, and then this will be the square root of 40 over 5. Now, negative 25 divided by 5, well, we can't hardly see that. Negative 25 divided by 5 is just going to be negative 5, and that's easy. And then inside the radical here, 40 divided by 5 is 8. Oh, but when I take a look at this, I know that 8 has got 2 as a factor 3 times. So like I know that this is the same as the negative 5 multiplied by the square root of 2 times 2 times 2. And that I can then take, okay, one factor of 2 out for that pair that shows up under the radical. So when I take that out and multiply it, well, there's a negative 5 out there right now, so that's going to be negative 10. And there was a 2 left over, so negative 10 root 2. That's the answer. That is this expression in its simplest form. And that's really what we want to do, okay? So the numbers might get a little bit more complicated, but that is the pattern. So here, split it up again. This becomes 45 divided by 9. Not is equal to. Just got to get rid of that little guy right there. Don't know why I did that again. Multiplied by the square root of 32 divided by 2. And that's easy. 45 divided by 9 is 5. And 32 divided by 2 is 16. Now this is a little bit easier than the previous one because 16 is a perfect square. I can take the square root of that to get 4, and then I know that 5 multiplied by 4 is simply going to be 20. Oh, so that expression reduces down to 20. That's nice. Here, okay, well, I like this one right here. This is nice. Again, the coefficients, just like our first question here, the coefficients are both 1. Okay, so I don't have to really do anything with that. So I simply put the two radicands together, and I know that I can cancel the b's. Now, normally we would talk about this in terms of restrictions as well. I can only cancel the b's, okay, as long as b doesn't equal 0. Okay, so there's a restriction here, but I can cancel those b's, and I'm left with the square root of a. Okay, so in other circumstances here, we're going to be a little bit picky about restrictions on the variables, kind of what you can and can't do, because there are times where you need to kind of throw up a red flag and say, I'm doing this, but I'm assuming that something is true. And in this case, I'm assuming b isn't equal to 0. Anyway, just something kind of log away for now. And then over here, again, we put the coefficients together, put the radicands together. Now this is the first time this has happened to us where we get a fraction as our coefficient, because 10 over 20 is just going to be 1/2. But 24 divided by 2 inside the radical here, that's going to be 12. But we have enough experience now, we've seen 12 show up. We know that 12 can be rewritten as 2 times 2 times 3. Okay, so that means I can take out a representative, a single 2, to represent that pair of 2's inside there. And so I've got 1/2 multiplied by 2, and there's a square root of 3 that I can't get rid of. But this works out beautifully because 1/2 multiplied by 2, I know that those are going to become 1, and so I'm simply left with the square root of 3. So that expression right there simplifies all the way down to the square root of 3. Okay, so we're going to do another example here, and like it says just above here, it says if you're able, simplifying a radical before dividing often makes the calculation a bit easier. And I would agree with that. So for example, for this one right here, we've got 2 root 27 over the square root of 12. Now I could do the division. I totally could, and please don't get me wrong. I can totally see how this would simplify a bit here. But I want to just take a look at what you would do here. One of the things that we could do here is just make these, split these radicands up. So 3 times 3 times 3, I know that that's 27. And 12, we just did an example like that, where that's 2 times 2 times 3. So I can pull out kind of our representatives. I can pull out 1, 3 for that pair of 3's. I can pull out 1, 2 for those pair of 2's. So the numerator is going to become 2 times 3 times the square root of 3. And the denominator will be 2 multiplied by the square root of 3. Well, now I can clearly see a whole bunch of things will cancel. Root 3 divided by root 3, 2 divided by 2. In fact, all I'm left with right now is a 3 in the numerator. Okay? That became a lot more obvious when I simplified. Now, I get it. You can, in a question like this, I mean, either way you do this, it'd probably be the same amount of work. So we're just doing this right now, just so you see it. Okay? Let's take a look at this next one. Same thing. Let's simplify it first. Okay? So this is 4 multiplied by the square root of 54. Okay, 54. I know 54 is 6 times 9. So that's going to be 2 times 3 times 3 times 3. Okay, so there's my 6 and there's my 9. And 8, we did 8 a few minutes ago. And I know 8 looks like that, 3 2's. So I can pull out a representative from that pair of 3's, and I can pull out a representative from that pair of 2's. So the numerator becomes 4 times 3 multiplied by the square root of 2 times 3. And the denominator becomes 3 times 2 multiplied by the square root of 2. Now, I could simplify this and make this 12 root 6 over 6 root 2. I could totally do that. But what I like about the work that I'm doing right here is that I can see that that 3 factor is going to cancel. I can see that the 2 is going to cancel with the 4 and leave me with a factor of 2 in the numerator. And then even right here, so that's the coefficient, okay, separate, completely separate from the radical. But even in the radical, I can see that I'm going to cancel those 2's, because remember, I'm going to put these under one radical symbol, and so the 2's will cancel. And what I'm left with in the numerator is a 2 and multiplied by the square root of 3. Those are the only two factors that actually survived that. Okay? Now, up here, okay, this one is going to be a little bit more complicated. Okay, so I've got an 8 here. Okay, well, 126. 126 divided by 2 turns out to be 63. 63 isn't divisible by 2, but it is divisible by 9 and 7, which means it'll be 3 times 3 times 7. Okay, 112, well, 112 is divisible by 2. And when you do that, you get 56. Okay, well, 56 is 8 times 7, so that's going to be 2 times 2 times 2 multiplied by 7. Okay, so I've got a pair of 3's up in the numerator, and I've actually got two pairs of 2 in the denominator. So in the numerator, I've got this 8 multiplied by a 3, and then I had 2 times 7 in the radical. In the denominator, I had two factors of 2 that popped out. And again, I can multiply that together. I could make that 24 multiplied by the square root of 14. Absolutely. I could make this 4 multiplied by the square root of 7. Totally. But I can see right now, I've got 4 in the denominator, 8 in the numerator, so that's going to cancel and leave me with a 2. The 3 stays. But even in my radical here, if I ignore the coefficient and just look at the radicands, well, that 7 is going to cancel. As soon as I put those together, that 7 will cancel. And so this is going to leave me with 2 times 3, 6, root 2. Because the 2 is what survives from underneath the radical. And there you go. Okay, next question here. It says divide each term in the numerator by the denominator and simplify. Okay, I like this question. It doesn't introduce anything new, okay? But it does force us to go back to a property of division that you would have looked at ages ago and kind of pull this back to the forefront of your mind here. When you've got root 20 plus root 40 minus root 90 all divided by root 5, what this means is this is the same as root 20 divided by the square root of 5 plus the square root of 40 divided by the square root of 5 minus the square root of 90 divided by the square root of 5. Okay, this is frequently something that people forget that you can do with division. We always understand that multiplication distributes. Well, so does division, really, in a way. So now I can put the radicals together in each of these terms. And so 20 divided by 5 is going to be the square root of 4. I like that. I can deal with that in a second here. 40 divided by 5 is the square root of 8. And I'm okay with that one. We did that one just a few minutes ago. And 90 divided by 5, that's going to be the square root of 18. And 18 is another familiar one. It's a small enough number that we've seen it a few times here. So the square root of 4, well, that's easy. That's just 2. 8 is, whoops, I wanted to write 8 underneath there again, but I'm breaking it up here. This is going to be 2 multiplied by 2 multiplied by 2. And 18 is going to be 2 multiplied by 3, right? 2 times 9. So I can take out a 2 there. I can take out a 3 there. So this becomes 2 plus 2 root 2 minus 3 root 2. Now, I'm not quite done with this question yet because notice that these two terms have the same radical. Now, if you think back to a previous lesson, I was talking about that. I don't know what the square root of 2 is. I haven't got a clue. But I know that if I've got 2 of them here and I take 3 away, I'm going to have negative 1 of them. It doesn't really matter what that number is. That rule applies. So I'm going to add together the like terms. So 2, and then this is going to become minus 1 times the square root of 2. And that's the most simplified way I can write this initial expression. Here, we're going to do the exact same thing. So this becomes 3 root 18 divided by the square root of 2 plus the square root of 2 over the square root of 2. I love that. That's just going to go to 1. You can see that immediately. Minus the square root of 12 divided by the square root of 2. Okay, so we just put the radicals together. The coefficient, there was no coefficient coming from the denominator, so that makes it easy. It's 1 in every case here. So this is just going to simply be 3. And when I divide the radicands here, I'm going to get 9. I don't even have to think about this one. Root 2 divided by root 2 is just 1. Anything divided by itself is just going to give you 1. And root 12 divided by root 2, when I divide the radicals here, radicands I should say, I'm going to get 6. Now, 6 is interesting. I can't do anything with it. It's got a factor of 2 and a factor of 3. That's it. There's no duplication, so that's it. That's as good as it's going to get. But 9, on the other hand, does have a square root. And the square root of 9 is 3. Since there's a 3 right here, when I multiply those two together, so 3 multiplied by the square root of 9, I am going to get 9. Plus 1 minus the square root of 6, and I can add together those like terms to get 10 minus the square root of 6. And now I'm done. Okay, now I want to talk to you about what happens. What happens if the radicals, okay, what happens if over here I've got something like, for example, the square root of 7 divided by the square root of 5. Well, what happens if I can't simplify that? What if they're not, I can't take 7 and divide it by 5? Well, is that the best I can do? And the answer is no, it isn't. Okay, I'm going to show you something here called rationalizing the denominator. And really, what do I mean by rationalizing? Most of the time when you have a square root of a prime number, or most numbers that can't be simplified into a nice result here, if I've got to have the square root there, it's going to be an irrational number. There are some reasons why having an irrational number in the denominator kind of doesn't make sense. Okay, let me put it like this way. It's easy to think of pi, because pi is a very common irrational number. Most people know that. I could take pi divided by 2. That makes perfect sense. I could draw a line segment that's pi units long and divide it by 2. That's easy. But what does it mean to take 2 and divide it into pi units? I don't even fully know what pi is. How do I break 2 into pi different pieces? It's a little bit hard to get your head wrapped around. So what we've done is this thing called rationalizing, where what we do is we get rid of the irrational number in the denominator. Now, it's not going to work with pi here, but it does work quite nicely with radicals. I'll show you. So let's say you've got something like root a over root b, and a does not divide by b. Well, then what I do here is, because this is the square root of b, if I simply square it, well, that's just going to cancel. It's just going to give me b. Okay, which is a pretty nice result. So I can square the denominator to get rid of that radical. But the thing is, if you multiply the denominator by root b, you have to multiply the numerator by root b. That's the only kind of little twist to this. This is the only thing that you've got to make sure that you do. So I'm going to square the denominator, but whatever I multiply by that denominator, I got to multiply by the numerator so that the whole thing stays equal. Because look at this. What is the square root of b divided by the square root of b? 1. So what did I end up multiplying by root a over root b? 1. Which means I didn't change the value. I did change how it looked. Okay, that clearly has happened. But I don't change the value of this expression, and that's what's important here. Okay, and now I've got this new irrational number divided by a rational number. That I can get my head around. That makes sense. Okay, let's take a look at some examples of rationalizing. So I see 1 over the square root of 5. So what I'm going to do is I got to get rid of that square root of 5 in the denominator. So I'm going to multiply that by the square root of 5. But if I do that down there, I've got to do it in the numerator as well. So 1 times the square root of 5, that's easy. That's the square root of 5. And root 5 times root 5, well, you can do this a couple of different ways if you want to. You can think of this as now the square root of 25. But regardless of how you come at it, it's still going to be just 5. That's it. Okay? Over here, I cannot simplify this 3 over the 7, okay, even if I was to try to put it under one radical. So I'm going to multiply by the square root of 7, multiplied by the square root of 7. I'm going to do it to numerator and denominator. In the numerator, root 3 times root 7 is root 21. In the denominator, root 7 times root 7, that's easy. That's going to give me 7. Okay, or you could think of it as root 49. but the square root of 49 is just 7. So either way, I'm going to get to 7. Now over here for C, okay, what I would probably do first here is take advantage of what we have learned just a few moments ago. I would simplify this first. Okay, I can do something with the coefficients first. I can simplify those. I can't simplify the radical. And that's the whole point of this section, is that the radical part won't simplify as nicely as I want. But I can simplify the coefficients. I know 8 over 2 is just going to be 4. And so this gives me this expression right here. Now I've got this square root of 3 in the denominator, so I'm going to multiply by root 3, multiply by root 3. So in the numerator, I get 4. Remember, 4 is the coefficient, so I'm not going to involve it in the multiplication of radicals. They're very different numbers here. But root 5 times root 3 will be root 15. And then down here, root 3 times root 3 is like the square root of 3 times 3, which means I can pull out a common 3 there. And there we go, 4 root 15 all over 3. That is a better way of writing this expression. Let's take a look at another one. Okay, 2 root 2 over 4 root 10. Okay, well, first of all, I can see that there's some relationship between the coefficients, but there's also a relationship between the radicals. Let's deal with that first. So this is like 2 over 4 and root 2 over 10. So 2 over 4 is simply 1/2. And then the square root of 2 over 10 is the square root of 1/5. Okay, well, and then I can split this back up to 1/2 and then root 1 over the square root of 5. But the square root of 1 is just 1, and I'm hoping that after enough practice you'll just be able to skip that. And so I'm left with 2 root 5, 1 over 2 root 5. So this expression is equivalent to this. But I don't like the way this looks with that radical in the denominator, so I'm going to multiply both numerator and denominator by root 5. And so that's going to get me root 5 in the numerator. Now, watch what's going on here. I've got a 2 multiplied by the square of root 5. Well, okay, root 5 times, just ignore the 2 right now. Root 5 times root 5 is going to be 5. And then there's a 2 down there also, so this becomes 10. So this becomes the square root of 5 over 10. Now, I know I did a little bit of back and forth with the radical here, right? Putting them together, simplifying, tearing them apart, and then rationalizing here. But like I said, the more you do this, the more comfortable you're going to get with it, the faster you'll be able to move through that. You'll be able to skip some of these steps as we go. Okay? So for example, this one right here, root 18 over root 5, I would make this root 18 over root 5. Okay, split that up. And then I already know that root 18 is going to be 2 times 3 times 3. At this point here, I'm not even worried about the fact that there's a 5 in the denominator. I will deal with that in just a moment here. Pair of 3's means that this is going to be 3 root 2 over the square root of 5. So now I've simplified the expressions. Now I'm going to take a look at that denominator because I don't like having that radical down there. So I'm going to multiply numerator and denominator by root 5. So in the numerator, that'll be 3, and then root 2 times root 5 will be root 10. And then root 5 times root 5 in the denominator is just 5. Okay? Okay, one more. Root 3 over root 12. Okay, well, what I might do here is simplify that root 12 to start off with. So remember, 12 is the same as 2 times 3. So I know that there's a pair of 2's there, so this becomes root 3 over 2. I'll take out a representative of that pair of 2's, put it out front, just a single one, and I get a root 3 there. Now, this was kind of a gift at the end here because notice I've got root 3 divided by root 3. Those are going to cancel. Notice that the 2 is still in the denominator. It didn't move up anywhere. It stays down there. So it's just going to be 1 over 2. So that was kind of a nice one to end that on because it worked out pretty nice. Okay, for this example, we're told to express each numerator and denominator in simplest form and then rationalize, which is what I've been doing here. It's just that these questions are kind of going to bump that up a bit of a notch here. So to start off with, 500. I got to simplify 500 here, the root of 500. Well, in this particular case here, although normally I would split this up in terms of all of its prime factors, the nice thing is I can see that there's a factor of 100 here, which is going to be 10 times 10. And I'm just going to leave it like that. Okay, because that's just easy to simplify. I don't need to spread that out more. That kind of fell into my lap here. And root 27, I've already seen a few times in this lesson. I know it's going to be 3 times 3 times 3. So I've got a pair of 10s there, so a 10 will come out, 10 root 5. In the denominator, I've got a pair of 3's, so I take out a 3, and there's a 3 left inside the radical. That looks good, except for that root 3 in the denominator, which I don't particularly like. So I'm going to multiply numerator and denominator by root 3. Now notice I don't care about the 3 in the front. That doesn't bother me in the least. I don't care about a factor of 3. I do care about a factor of root 3. Okay? Because I'm not 100% sure how big this root 3 is. I don't know if I can ever be 100% sure what it is, other than the symbol root 3. So now, my numerator, when I multiply those together, I'm going to get 10 root 15. Okay, because root 3 times root 5 is going to be 15. Remember, I don't multiply by that coefficient there. And then 3 multiplied by root 3 by root 3. Well, root 3 times root 3 is going to be 3. We've seen that a number of times today. Multiplied by 3, whoops, is going to give you 9. And so this expression here can be written as 10 root 15 over 9. Okay, similar sort of thing here. I got to simplify down this 240. But as it turns out, 240 is actually similar to that 500 here. I know, and this is maybe just the geek in me popping out here, but I know that 240 is divisible by 16. Now, we could break this up into its factors if you wanted to. I could look at that and say, wait a minute, okay, I know that it's divisible by 2, by 2, by 2, by 2. And in fact, if you did that, you would exhaust the 16. And then it's divisible by 3 and 5. But I knew it was divisible by 16 to begin with, so I could have jumped right to that. And then 108, same thing. I mean, once you've done this a bunch of times, you get fairly comfortable with this. And you will see that 108 is going to be 2 times 2. Okay, whoops. Times 3, whoops, times 3, times 3. Okay, it ends up actually being 36 times 3, so 6 times 6 times 3. Now, that aside there, hoping that you've done this enough that you know, I'm going to take out a 2 for that pair, a 2 for that pair. And in the numerator, that's going to leave me with root 3 times 5. In the denominator, I'm going to take out a 2, and I'm going to take out a 3. And that's going to leave me with a square root of 3. Okay? Now, in this case here, when I look at my coefficients, a factor of 3 will cancel, a factor of 2 will cancel, so I'm left with a 2 in the numerator. The 3's will cancel there, and that root 5 stays. So this is great. I didn't even have to rationalize this one. Just the fact that I simplified it allowed me to get to this form right here. And I've got no problems with that right there. I have no problems with a root 5 in the numerator. That's wonderful. Okay, now our final question here for this lesson here. We're going to take and simplify the radical expression. We got square root of 100 minus the square root of 28 over the square root of 2. First of all, we're going to rationalize the denominator first. Okay, so what that means here is we're starting with root 100 minus the root of 28 all over the square root of 2. Now, immediately, I mean, I see this root 100 and I want to simplify that right away, but what we're going to do is we're going to rationalize here first like we're told. So I got to square that denominator. I'm going to multiply by root 2, and I'm also going to multiply the numerator by root 2. Now, the single most common error, and we warn students about this all the time, but it's very hard to get people to stop, is I need you to distribute both of these terms with this root 2. Both of them. Okay? Not just the first one. Or depending on how you write it, not just the second one here. So the denominator here is clearly going to become 2. Okay? Root 2 times root 2 is going to give me 2. But when you distribute this, this is going to become the square root of 200. Okay? Because you multiply the radicals together. The radicands, I should say. And 2 times 28 is going to be 56. Okay, so we had to do that first, and you had to distribute the root 2 to both those terms. Now I'm going to simplify, and I know this first term is going to be 2 times 10 times 10. I mean, I saw the 100 there, and I was anxious to simplify that immediately anyway. Minus, well, 56 is 8 times 7, so it's going to be 2 times 2 times 2 times 7. Okay. And I mean, you just get used to some of those numbers. 8 is just automatic. I mean, I know it's 2 cubed there. So I'm going to take those 10s and pull a 10 out. I'm going to take those 2s and pull a 2 out. So this is going to become 10 root 2 minus 2 root, now I'm still left with a 2 times a 7 in there, so I'm going to leave that as 14 all over 2. Now to finish this off here, this looks fine, okay? Except for the fact that both of the terms in the numerator are divisible by 2. Now, if you think back to something we did just a few moments ago, remember, I can distribute that division to both of those terms. So I can make this 10 root 2 over 2 minus 2 root 14 over 2. Now, in both cases, because the denominator does not have a radical, it's just a whole number in this case, well, I can just divide the coefficients. So 10 root 2 over 2 becomes 5 root 2. And then minus 2 root 14 over 2. Well, the 2's cancel. I'm just left with minus the square root of 14. And that's the answer that we're looking for. The other way to do this is I'm going to divide each term in the numerator by the denominator first. So then this was going to become, this expression up here was going to become the square root of 100 divided by 2 minus the square root of 28 divided by 2. Okay, well, the square root of 100 over 2, that's just going to be the square root of 50. And the square root of 28 over 2, that's going to be the square root of 14. Okay, well, these are nice smaller numbers here, so I'm comfortable with this. I know that 50 is 2 times 25, which is 5 times 5. And I know that 14 is 2 times 7. And so there's no repetition in the roots there, the factors I should say, so that's as good as it's going to get, root 14. But here I can take out a 5, make that 5 multiplied by the square root of 2 minus the square root of 14. Okay. Notice that this was a faster way of doing that. So it's up to you kind of how you want to approach it. The more comfortable you get with these, the quicker you're going to get. I hope the division here makes sense. And just bear in mind as you kind of proceed with this that there are other little issues here that this is going to build on it. We've got other lessons in the future that will build on what you're learning here.